Okay, we are on take 2 for chapter 4, lesson 4, similar triangles with problem solving. Sorry again that the last video did not have any sound attached to it. I'm not really sure why that happened, but we'll deal with some problem solving in this unit, or in this lesson, I guess. If you have not completed the lesson 3 video for similar triangles basics, I need you to finish that, and I need you to finish the practice before you move on to lesson 4. Some of these questions aren't really going to make sense if you haven't watched the lesson 3 video yet. So you're going to look at the lesson 3 first, finish that practice, and then come back and start this. So this is a ladder leaning against a wall problem. These are pretty common types of questions, so I want you to make sure that you are really familiar with them. So this first one says you have two ladders leaning against a wall at the same angle. That's an important point, that it says that they're at the same angle. One ladder is 4 meters long and reaches 4.2 meters up the wall. The second ladder is 9.2 meters long. How high does this second ladder reach up the wall? Complete and label a diagram to help. So they're at the same angle, that's important. And so we have some important information. So there's the angle, that's the same. And another angle that we know for sure is the same is that the wall is a straight wall. It's standing straight out of the ground. And so the wall is at a 90-degree angle. And so those are two angles that they share in common. And so therefore that other angle at the ground is also a shared angle. So these are similar triangles. So we're going to use that information to help us solve a problem. So we're going to label the rest of the information onto these triangles that the problem told us. So the 4 meters long is the length of the ladder, so we can add that onto our drawing of the smaller ladder. And this would be the hypotenuse length. And so if we stood that ladder standing up, it would actually be 4 meters tall, but it's slanted. So it's a 4 meter tall ladder, and it hits the wall at 3.2 meters. So we draw 3.2 meters, that's the height on the wall. We don't know how far away it is from the wall, but we don't need that information right now. And then the second ladder, again, if it was standing straight up, it would be 9.2 meters. So we've just turned it on its side. And we want to know at what height does it hit the wall. Our answer should be less than 9.2 meters, but should definitely be greater than 3.2 meters. And so I would recommend redrawing these two triangles away from the situation with all the important information labeled. So they're going to look something like that. You might want to pause it and draw those on. And so we have two similar triangles. We want to use the fact that they're similar to find out what the missing side length is using the corresponding side lengths. And so that bottom angle would also be the same. So we know that it's a similar triangle. And so we are stating that because all the angles not really sure why I stopped writing there. Oh, okay. Because the angles are all the same, the triangles are similar. So because the angles are the same, we know the triangles are similar, so we can use that to use a scale factor with the corresponding side lengths to find our missing side length. So the two side lengths that we know for sure that correspond are the hypotenuses. Hypotenuse? Not sure. Anyways, the two lengths of the ladders, the 4 meters and the 9.2 meters, are the corresponding side lengths because they're both the hypotenuse of these similar triangles. So we need to think, what's the scale factor? So 4 times something gave us 9.2. In order to find our scale factor, we can work backwards. So 4 meters is associated with the 3.2 meters, and the 9.2 meters is going to be associated with our unknown. So we're going to set up like a equivalent fraction type scenario. You don't have to set them up as fractions, but I'm just showing you another strategy. And so we're thinking, what do we do to 4 to turn it into 9.2? Well, we can work backwards, and we can go 9.2 divided by 4 to find what the scale factor is. And so when we divide those, we find that we need to multiply. Oh, see, there I am showing you. Okay, so we need to divide by we need to multiply by 2.3 in order to make the proper enlargement. And sometimes your scale factor might be a decimal. That's not an issue. That just happens sometimes. And so if the hypotenuse has been enlarged by 2.3 times, that means the wall height will also be enlarged 2.3 times. And so where the taller ladder hits the wall is 7.36 meters. So it works. It's less than the 9.2 and it was greater than the 3.2. So the 9.2 meter ladder, long ladder, reaches 7.36 meters up the wall. And this is actually an important question that you would use in real life, because ladders do come in different lengths and you do need to reach things that are at different heights. So knowing which ladder to use to get to whatever you need to reach is actually important. So you will use this in real life. Or if not, you might be one of those people that stands on the top part of a ladder and then falls off. And then I need to come visit you in the hospital because you fell off a ladder. And I don't want to do that. Okay, here's the next type of example you see a lot. So we like to talk about shadows. And so we have Ned standing in front of a tree and the sun is behind them, so the shadows are being cast out kind of in front of them to the right. So it says Ned is 1.4 meters tall and he casts a shadow that is 1.2 meters long. His shadow reaches to the end of a tree shadow when he stands 5.25 meters from the tree. We're going to complete the diagram and figure out how tall the tree is. So when you read something like that, it's important to read for understanding and pull out the key terms and pull out the key information and start labeling it. So his height is 1.4 meters, and we are assuming that he is standing straight up, so he is making a right angle with the ground, and his shadow is 1.2 meters long. So we drew those two amounts in, so we're dealing with right triangles again, and the tree is also growing straight out of the ground, so it makes a 90-degree angle. And the distance of the shadow, we don't know, but we do know from how far away Ned is standing from the tree, and we know that he is 5.25 meters from the tree. So we can easily figure out how long the tree's shadow is altogether if we add those two lengths up. And so we want to know how tall the tree is, and so we're going to use a variable. In this case, we're going to use t, because trees start with t. You could easily just use a question mark again like last time. It's not a big deal. If you are going to start using variables, make sure you identify them and what they stand for. So somewhere on here I should have put t equals tree. I didn't do that, so I would lose 0.5. So you want to make sure you do that. So we're going to redraw the triangles again, labeling the important information. Excuse me. So this is the larger triangle for the tree, and so the full length of the tree shadow is 5.2 and 1.2. And we should point out that I made a mistake here. He is 5.25 meters, so that actually is 6.45 meters, his shadow. I will fix that in a couple seconds. I remember I went back and did that. And so then we draw the smaller green triangle for Ned, his height and his shadow length. And so in this case, it's the hypotenuse length that's not important. We could find it if we wanted to using Pythagorean, but we don't need it, so we're not going to worry about it. We are going to figure out which sides are corresponding sides. And so the two corresponding sides are 1.2 and 6.4. And it's actually 6.45 meters, right? And the height of Ned, 1.4 meters, corresponds with the tree height. So again, we set up two equivalent fractions, and we need to figure out what scale is used to make those. Oh, here we go. That's where I'm fixing my mistake. So we need to find out what scale factor is used to make sure that those are consistent. So using the 1.2 meters and the 6.45 meters, we need to figure out what the scale factor is. So we're going to divide 6.45 by 1.2, and that tells us what needs to get multiplied. So we need to multiply by 5.375. And so if we do that on the bottom, in order to keep an equivalent fraction, we do the same on top. So we are going to multiply Ned's height by 5.375 to find out what the tree height is. Okay, and so when you multiply those, you get a tree height of 7.525 meters. And so again, on word problems, it's always good to add in a sentence explaining what your answer is. So the tree height is 7.525 meters tall. And on an example like this, we could use the fact that the angle at the ground is the same for the shadow. So that's how we know the triangles are similar. So this similar triangle problem deals with a ramp, and again, 2 different heights of ramp. I'm going to leave this problem for you to try on your own, as it's very similar to the ones that we just completed. But this next one is a little bit different. So I want us to talk through these examples because you haven't seen any like this just yet. So whenever you have a triangle inside another triangle, the angles are the same. So angle A and angle D will be the same, angle C and angle E will be the same, and then angle B at the bottom is the same for both of them. And so we have a smaller triangle ADE inside a bigger triangle ACB. And okay, so the angles are the same, so we're dealing with similar triangles. We're going to use that information that the triangles are similar to find out what the missing side lengths are. And so here I'm just pointing out the angles that would be corresponding. So A and D, C and E, and then B is the same angle for both triangles. So I hope you notice that BDE is actually B to D and D to E are the same length. And so this is actually an equilateral triangle. And so B to E will also be the same length, 1.9. Anyways, we're going to use the corresponding sides to find out what the missing side lengths are from A to D. So yeah, similar, there we go, equilateral triangle. And so we need to know, so AC and DE are the corresponding side lengths. They have the same angles on both ends of those side lengths. And B to D and A to B are the same. And so if the inside triangle is an equilateral triangle, the outside triangle is also an equilateral triangle. So all the lengths are 2.9. So the missing length from A to D is just the difference between 2.9 and 1.9. And hopefully you remember difference means subtraction. So that length would be 1.0. There's no units, so we don't need to include units on our response. Okay, so looking at the next example, again, we have a triangle inside a triangle. UVW is inside UYZ. And so they're going to share the same angle, so they are similar triangles. So we need to find the corresponding side lengths in order to find the missing side length of X. So UY is going to correspond with UV. So 11 and, there we go, yeah, UY, UV. 11 and 25.3 plus 11. Okay, so we get corresponding side lengths of 11 and 36.3. So we can use whatever that scale is to figure out what X is going to be in relation to the 33 along the bottom. And I'm actually changing the ratio to a dot dot for the ratio versus an equal sign because they are more, it is a ratio, not an equals. 11 does not equal 36.3. So that is technically not a true statement. But if we put it as a ratio or as a fraction, then it helps us see. So we're setting up the ratios 36.3 and 33 go together, and 11 and the unknown side length go together. So we need to figure out what do we need to do to 36.3 to turn it into 11? Well, we need to divide. So we're going to divide just to kind of see what that factor is. And then we're going to multiply by 1 over that factor because it is a division, so it's a reduction. And so you need to divide by 3.3, which is the same as multiplying by 1 over 3.3. Now, because this question doesn't ask for the scale factor, we can actually just show that you need to divide. And so when we divide, we get 10 for the missing length. So that's it for this practice. Again, apologies for no sound. And you'll have some time in class to do some practice of these.